Happy prototyping, everyone! The project for this video is a laser engraver. To understand what we're doing, we first build a 3D model in OpenSCAD. This has two advantages. We can see what's going on and model every detail. We need to understand that everything is right. And later we can use this model for printing. The metal bars and motors we can then order from OpenBuild. Here we can see the process of printing the parts after we finish the model. Good practice is to have iterations. Every time you see you have a fault in your design or something is not working as expected, you can update the model and then, for example, print the parts you have changed again. For this project, I actually printed one part 3 times. And I actually didn't record every time lapse for every part I printed, just the most interesting ones. For this time lapse, I actually recorded one picture per layer. The other recordings are speeded up by a factor of 30. Now to the electronics. First, we need a driver circuit for the laser diode. There I had two goals. The first goal, that I have a mode where I can use the laser without my safety glasses. The problem there is that the laser shouldn't emit more than 1 milliwatt. But the laser I ordered from Banggood had already an electronic inside. So with the electronic inside, I couldn't go down to 1 milliwatt. My second goal was to have very high switching frequency. But also the electronics in the laser didn't support that. So I decided to build my own. So I end up using a current source with 2 amps for the high power mode and just a resistor for the low power mode. And I also used a MOSFET for the high frequency switching. I tested the whole circuit and the results looks very promising. Here you can see the circuit for the high power part. Now we need a possibility to control the stepper motors. I looked around for a suitable firmware for the task I want to achieve, and I decided to use GRBL because it has a really stable code base and is not so complicated to understand as Marlin or other firmwares they are used, for example, for 3D printers. That was important for me because I had to make some changes. The first change I need is to have two separate controllers for the epsilon axis because I use two motors. And for the homing, I need to home them separately. The second modification I needed was a way to control the laser. Version 1.1 from GRBL actually supports a laser mode, but I decided to use a separate axis for this task. So I introduce a new axis A by side from X, Epsilon and Z. There was a lot of problems. It is actually really easy to add another axis to the GRBL, but then the firmware treats all the axes the same. So if a speed change happens on the A axis, also the other axes are slowed down. This behavior for a laser is actually really counterproductive. My idea is to use the pulse output from the firmware to not control a stepper driver, but directly control the output of the laser. So what I need is actually that every speed change or rate change on the A-axis should not have any influences on the other axis. But if there are too much pulses per distance, the other motors have to be slowed down. In the end, I achieved to make the changes and they turned out really nice. GRBL is actually using a timer interrupt to generate the pulse lengths for the pulse for the stepper driver, or in my case, the pulse for the laser diode. So I actually could make the pulse for the laser diode longer. And there is also the mode that when the laser is in full speed, that means that there is the maximum number of pulses per second. I achieved to manipulate the interrupt in a way that in this case the pulse output will be constant high. I also changed the numbers for the A-axis from absolute to relative. So in the end, if you have a move from one position to the other, you just tell with the A parameter of the G-code how much pulses you want to have over this distance. So the firmware will automatically slow down if there are too many pulses and they will come over the maximum pulse rate, or keep the speed and spread the pulses evenly over the distance. If someone is interested in the modification of the firmware, I posted all the changes to my GitHub repository. Links to the GitHub repository and the hardware repository will be posted in the description. Now to the hardware assembly. I bought the wood from a local hardware store. There you can give the exact size and they will cut it for you. It costs, for me, it cost around 10 to 15 euros. To be on the safe side, I decided to make a full enclosure so that it is not possible that some laser light can escape and damage my vision. A laser with this power grading is really dangerous. You can be blinded in a fraction of a second. So I also included safety switches. When you open the lid, the laser will be shut off immediately. The problem with a full enclosure is that the moving height of the Z-axis depends on the size of the whole construction. So if you want to have, for example, moving height of 20 centimeters, the enclosure have to be at least 40 centimeters. That was too big for me. But I also didn't want to restrict my object height for things I can engrave. My solution for that problem I came up with is to use wooden rings. So if I have an object what is under 5 centimeters of height, I don't use any wooden ring. If it's over 5 centimeters, I use one. If it's over 10 centimeters, I use two, and so on. So therefore, I can dynamically change the height of my full wooden enclosure and can use it to engrave different objects with different heights. Furthermore, the whole design is optimized for speed. So I use big stepper motors. In this case, there are NEMA 23, and I use also high power stepper drivers. The problem with stepper motors is the higher the speed you run them, the less momentum they get. So if you want to run something at high speed, you need a lot of extra momentum. I also use pulleys with a higher teeth count to that I get more distance for less steps. The only problem here is the resolution. The less steps you have, the less resolution you get. So there is some way a trade-off between speed and resolution. But don't worry too much about this trade-off, because most stepper drivers can do micro steps. So in the end, if you see that the resolution is not enough, you need higher resolution, just turn on micro stepping on your stepper driver. The bad side about micro stepping is that you also lose momentum. So you can change this dynamically. If you have something what needs higher speed, and less resolution, you can just change the settings on your stepper driver to go, for example, full steps. This gives you more momentum, but don't have so much steps per millimeter. And also the other way around, if you want to go a little bit more slow, but you need higher resolution. The next problem you have to be a little bit careful about is stability. When you're moving with high speeds, you have also a higher force when you change, for example, the direction or change the angle of the move, of the next move. The firmware actually tries to make this force, to limit this force in a way that it is controlled. But the more you have to limit the force, the less speed you get in the end. So when your goal is to go higher speeds, you also should considering to make the design as stable as possible. That's why I decided in my design to use two roads for the x-axis. The most problems I actually had with the z-axis. I want the z-axis to be controllable. Like a lot of laser cutters actually have a fixed z-axis. So you have to adjust them before you start engraving or cutting, but it cannot be changed during the cutting or engraving process. But when you have a controllable z-axis, you can actually engrave or cut around or out of angel objects. And this gives a really big flexibility of objects you can work with. So my solution I came up for this problem is to actually use a really small NEMA 17 and a linear gear. The linear gear is directly mounted to the metal rod, and so the NEMA has also a gear, and this is directly connected to the linear gear of the rod. So for the z-axis, I don't need a bell. I just need the guidance for the metal bar. So my z-axis turned out to be really compact. And this means it doesn't have so much mass. Therefore, it's also really nice if you want to operate with higher speeds. Now the assembly of the X and Z axis is nearly finished. One important stuff is to have a high tension on the belt. Every play on the belt will result in a backlash in the end. You also should be careful about exhaust fumes, because when you operate the laser and engrave or cut materials, they are getting really hot. So for example, when you process wood, it actually will burn. Or when you process plastic, there can be some dangerous gases released. So you should be considering that you have a lot of fresh air when you're working with a laser. Or in my case, I don't have this possibility. I decided to use an active coil filtering system. So I ordered an active coil filter, and I also have a ventilation system. So the air from my enclosure, from my wooden enclosure, is sucked out into the filter. The active coil filter is really efficient, but you have to be careful which kind of filter you order. Just to be on the safe side, don't buy the cheapest one. In the end of the assembly, my camera actually broke, and I didn't have all the video material. So the mounting and the cabling of the electronics, I actually don't have a time-lapse video. I'm really sorry about that. To supply the electronics and the stepper drivers, I decided to use a 12 volts 10 amps power supply from Banggood. I had some problems because the first supply I got actually burned on first connecting to mains power. So keep in mind, if you order some gadgets which actually plugged into mains from a Chinese supplier, be really careful and really know what you're doing. It's normally not fail safe, and in some cases they actually have really big problems with mains isolation, so it can also be really dangerous. I decided to mount a camera to the Z-axis, so if the whole system is closed and the laser is running, I can actually see what's going on inside. Another thing I mounted on the Z-axis is a switch. The switch is connected to the probe pin of the firmware. So if I have, for example, a round object or something what is not completely even, I can make a height profile. And with this height profile, I can then, during the engraving, correct the height for each move and therefore get much better results in the end. To control the laser and to do, for example, the height mapping or the conversion from an image to the G-code for engraving it, I use a software called CNC G-code controller. I developed the software myself. The idea for this software is actually coming from the problem to use an firmware optimized for 3D printing for other tasks, for example, to control a CNC machine. And the problem is that the G-code of a CNC machine is not the G-code a firmware optimized for 3D printing is expecting. In the last years, I added a lot more new features to this software. One feature is, for example, the auto leveling. Another feature is path optimizing, and now support for laser engraving. This software is also open source, and I will put a link in the description. You can find it on my GitHub account. The details about how this software is working and how to control the laser or a CNC machine with it will actually blow up the frame of this video. So this may be part for another video. Now we nearly finished with the assembly. The last stuff I'm doing right now is to mount the switches to recognize if the enclosure is open or not. This is actually really important because when the laser is running and you open the enclosure, there should be no danger at all. So I actually mount two switches, one for each plate. The two switches are wired in series. If one switch is turned off, the laser will turn off immediately. So it is actually a redundant system. So if one switch fails or something, it cannot happen that there will be a problem. The whole project turned out really nice. Here you can see some of the results of the engraving and cutting.